Hi everyone, we're just going to do another lesson on motion graphs and two specific scenarios that we're going to look at are these ones here. I'm going to be using virtual physics just to have a look at the wee simulations that are on here. So the first one is the bouncing ball, and the second one is just an object that's been thrown upwards. Okay, so it's ball being dropped basically and bouncing, and the ball being thrown directly upwards. So we'll take the bouncing ball first of all. And these graphs are similar to the graphs that we've seen before. So this is the graph for the bouncing ball. So you might want to pause the video just now and have a wee think about what the video might look like. What the graph might look like. So you've got your velocity on the y-axis here, time on the x-axis. Right, so we can see the ball being dropped, and the graph is produced at the same time. So it bounces once, bounces a second time, and back to the original position. So in terms of the, if we just take that back to the, it shows you two different versions of the graph. The first one is where there's no energy lost. We'll just discuss that one first. So points that we can note on the graph. What I'll do is I'll just identify a few key positions on the graph, and we'll talk about where the ball would actually be at those different points on the graph. So I'll mark those in just now and then we'll discuss those. So I've just highlighted one bounce, if you like, so one cycle. It's half of the full graph, because remember there was two bounces before it then came back up to the original position. So I've just highlighted one bounce basically, okay, and then the cycle just repeats from there, okay, and it would just continue to repeat if you were to allow the ball to bounce. So this is it obviously at the highest point, just before it's released. So velocity is 0, but then the velocity begins to increase, so it's accelerating towards the ground, reaches its maximum speed here, and at this point here, it's in contact with the ground. Okay, so that's the ball hitting the ground. So what's going on there? What you're seeing is it's drawn, the line's drawn so it's almost vertical. And that's because over a very short period of time, this is the bounce, it doesn't last long, the velocity changes very, very quickly. So it's a really high magnitude of acceleration or deceleration and then subsequent acceleration. And during this time, the velocity of the ball decreases to 0. That's the force from the ground that's causing that. So it's decelerating till the velocity reaches 0, and then the velocity quickly changes to become a negative velocity, so then it accelerates in the negative direction and then comes up off the ground here. Okay, so if there's no energy loss, then this magnitude of velocity should be the same as the one that was up here. Okay, so say the ball had reached, let's say, we put a value in here, and we put a value in here, those two magnitudes should be the same. So if we said that the ball had reached a speed of 4 meters per second just before it hits the ground, then it comes back up off the ground at minus 4 meters per second. Okay, but all that happens really quickly. So that's what they're trying to show in the graph here, just with this really steep line. Okay, obviously it can't take no time, so it can't be completely vertical, but there's a very, very short time interval here between which the velocity goes from plus 4 meters per second to minus 4 meters per second. And that's what happens when you have something hitting the ground and bouncing back up. So it should come back up at roughly the same speed as what it hit the ground. So that's because the force on the ground has come into play. Prior to that, it was just free falling, okay, under the force of the weight of the ball, which means the acceleration should be 9.8 meters per second squared. And then what we see is you get the force from the ground taken over, so that creates a large unbalanced force upwards, which causes the speed to decrease, the velocity to decrease, but then to continue to decrease, essentially to become a negative velocity, and then it comes up off the ground here. Okay, so it's now coming up off the ground with a a negative velocity because it's moving up the way. You can have this graph drawn the other way because we've kind of broke our normal convention, and what we're saying is that downwards is positive. So when the ball was falling downwards, it's got a positive velocity, and when it's coming back upwards, it's got a negative velocity. So that's not the convention that we would normally use, but that's what they've used for the graph. So they've said that downwards, any vectors that act down the way are positive, so that's why the velocity is positive in the first part of the graph, okay, and then negative in the second part of the graph. So like I said, you can swap it round and change the convention, and your graph would just start off here, and then it would increase in the negative direction, and then do that, and then basically it's like the reverse of that. Okay, so it would be reaching a downwards velocity of -4 meters per second, then changing to become +4, and then it would decelerate to 0. Okay, so that just depends on what you're deciding on which direction is positive. So they've used on this graph downwards to be positive, and then the cycle just repeats after that. Other things we can do with the graph, obviously it's a velocity time graph, so if you work out the area under the graph, then it should tell you the displacement. Okay, so area under a speed time graph tells you distance, area under a velocity time graph would tell you the displacement. But we've looked at ones like this before. If you work out this area here for the triangle, and then this area here for this triangle, if you add those two together, you'll get 0. Okay, and that's because the ball has fallen, bounced off the ground, come back up, and it's back where it started, so displacement should in fact be 0. So that's just an explanation of the graph for the velocity time graph for the bouncing ball. The reason this one is a bit different is because, unlike the ones we've looked at before, where, for example, the trolley's rolling down the slope or it's rolling up the slope, there's only ever one force that's causing the change in the motion, normally the force of gravity. Whereas here we've got the force of gravity acting for the first part of the motion, and then we've got the force from the ground acting on the ball, acting on this part of the motion, and then back to the force of gravity. So this is the bit that's new, having this large unbalanced force acting on the ball just for a very short time, which kind of flips the motion. It makes it go from positive velocity to a negative velocity almost instantaneously, and then it's just the weight acting on the force of gravity acting on it as normal. Okay, hope that makes sense, guys. We're going to have a look on the next slide at the ball thrown vertically upwards. Right, okay guys, let's get a look at this this simulation here. So it's the object thrown upwards, ball thrown upwards. So we can see here that the simulation is a wee bit clunky. So it's just showing you the ball being thrown upwards. Just going to play it until, so that's the ball just now back down to where the person has thrown it. So that should be quite a familiar graph to us, because it's the same shape of graph that you would get for the, don't know if you remember the one where the car was moving up the ramp. So if you had your smart car on the ramp, but you pushed it up the way, so you gave it an initial velocity here by pushing it or releasing the wee piston that fires from the trolley, and that would then give it a velocity acting up the way, but then the weight of the gravity of the force of gravity on the trolley makes it slow down and then roll back down the ramp. So that's kind of the same shape of graph that we've seen for that one. The only difference really is that you've just thrown it upwards, and so the full force of gravity acts on the ball, and so you should get a steeper gradient, if you like, or steeper, greater acceleration, because your acceleration is going to be minus 9.8 throughout this. Okay, so they've gone back to the normal convention. They've just swapped things around from the last slide. So we're back to saying that upwards vectors are positive. So that's why when the boy throws the ball up here, the initial velocity is positive. And obviously with the weight acting downwards on the ball, okay, so as it falls, the weight is always acting in the, well, downwards, which is opposite to the direction that the ball is originally moving. So the ball's originally moving upwards when he throws it. And and so your weight opposes, the unbalanced force opposes the motion, right, which makes it slow down. Okay, so deceleration here to begin with. Then at this point, this is the ball at the highest point. Okay, so that's where v equals 0. So that's your highest point before the ball falls back down again, and on the way back down it's accelerating but in the negative direction. Okay, so your velocity goes from being positive to 0 at the highest point, and then it becomes negative, but it's accelerating during that phase. Okay, so decelerating here, accelerating here, but the acceleration remains minus 9.8 throughout, because remember, a negative acceleration when the velocity is positive makes the velocity decrease, and makes it go towards 0, and then a negative acceleration acting on the ball from there on a negative velocity will make the speed increase. The velocity is still decreasing because it's becoming more negative, right? So that's still a decrease in the velocity, you would call it, but the speed's increasing, so it's accelerating. Okay, so basically a negative acceleration is always going to make the velocity decrease, right? And mathematically that's always decreasing. Okay, even though here the speed's actually increasing, the velocity's decreasing because it's becoming more negative. That's a decrease in the actual velocity. Okay, so we'll have a wee quick look at the corresponding acceleration time graph just so we can match that up. Right, so that's the acceleration time graph there, and we can even add the value because we know that as the ball is falling, right, it would have an acceleration of minus 9.8 meters per second squared, and that's throughout the motion. Okay, so that gradient there doesn't change, it's minus 9, it's a negative gradient, right, so you can see that as well when you look at the slope on the graph, so it's negative gradient throughout, and that gradient is minus 9.8. Okay, which makes the velocity decrease to 0 and then continue to decrease to become more negative. But remember, we've got an acceleration here and a deceleration here. Okay, just having a look at the end of the clip. So this simulation actually allows for the ball to fall below the original position. So that means that this part of the graph is bigger than that part of the graph, so it's allowed to fall a little bit further than where he threw it up. Okay, and you can see that just by looking at the size of this area here. Right, so that area is smaller, this area is larger, and that's because that's representing a bigger distance, if you like, from the top. So that's from the highest point, right down to the lowest point here, right, when it hits the ground. So that area there you can see is bigger than the one up here. So in the normal situation where you've got, we'll just take it back. So normally the ball would, if the ball goes up and then comes back to the original position, we can just take it back. Then if you were to work out the displacement, it's actually just gone below the original position there, but if you were to work out the displacement by calculating the area, then you've got a displacement of 0, because the two areas, let me just pull it back a wee bit there, so if you imagine it here, that area would be the same as the one above, so your displacement would be 0. In other words, it's gone up and back down to where it started, but in this simulation they're allowing it just to drop below the starting position. Okay, so your displacement would actually be negative there, because you're going to have a larger negative area here than you have your positive area at the top here. So when you add these two together, instead of getting 0 this time, you're going to get a negative displacement because the ball is now actually lower than when it started. So I hope that makes sense. This one should be familiar to you already because it's the exact same motion graphs that you would get if you had the trolley rolling up the slope and then rolling back down again.